We will model a two-server queuing system which follows a Poisson arrival process and a exponential service time distribution. So we have a company which is run by Martin and Ellis, which offers services in cybersecurity technical support. And everything is made available over phone. And the arrival rate of the calls follows a Poisson distribution, which has a hourly arrival rate of 60 calls per hour. And the inter-arrival time can be calculated from this. We will just soon see it. Similarly, the two employees here, Martin and Ellis, they have their respective service performance rates. So Ellis is more experienced and provides faster service than Martin. So Ellis serves about 36 customers per hour, which also follows a exponential distribution. And Martin follows services 30 customers per hour. There is also a priority order which is built into it, wherein if both Ellis and Martin are free, the call will always be prioritized to Ellis. If Ellis is busy, then the call goes to Martin. And if both of them are busy, then the call is routed to whoever becomes available first. Right? So we want to, in a typical shift, they handle about 500 customer calls between Ellis and Martin, 250 each. And we would like to kind of calculate the queue performance parameters for each run, and then average it over 100 runs to arrive at the overall long-term queue parameters. So let's start. So let's begin with the first set of calculations. So arrival parameters, you receive the average calls. I can just change it to calls. Calls per hour is 60. So average number of calls per minute is 60 divided by 60 minutes, because there are 60 minutes in an hour. And so the average minutes for inter-arrival, right? If you receive a call per minute, so what is the inter-arrival time between this, the average minute between the call, right? And that's what we can call it as inter-arrival time as well. Right? Let me call it as inter-arrival time. And that will be the inverse of this, 1 divided by average calls per minute. Similarly, we can calculate it for the Ellis, customer served per hour. So the customer served per minute is divided by 60, and the average number of minutes that each customer will take will be 1 divided by 0.6. And so on an average, every customer, it takes 1.66 minutes. We'll calculate the similar we'll do the similar calculations for Martin as well. Equal to 30 divided by 60, that's 0.5. So the average minutes each customer takes is 1 by 0.5, that is 2 minutes per customer. And we know that Ellis takes us 1.66 minutes on average to service a customer, and Martin takes 2 minutes, a little longer than Ellis. So we need to kind of calculate these performance parameters of Ellis and Martin, and we'll calculate the single run parameters of the queuing system, and then we'll average it 500 times to calculate the 100 run based averages. So these would have more reliable values compared to what you get to see in single run. So now we know that the average inter-arrival time is 1 minute. So let's look at the Poisson distribution of the inter-arrival time. So what I have done is I've kind of inter-arrival time, I have created a table wherein the inter-arrival time can go from 0 to 60. Since the average it at 1, so you would unlikely see very large inter-arrival times. I mean, you're unlikely to see like a between customer 1 and the customer 2, the time difference is 15 to 20 minutes. Uh, that's going to be very unlikely. So to calculate the Poisson distribution, we use the Poisson distribution function, where we look at what is the probability of two customers arriving at the same time. And characterized by the parameter which tells us the average inter-arrival time, comma, and since we're going to use a lookup function to see these values, so I will use the cumulative function. So there is a 36% chance that you will see two customers arriving at the same time. Right? You can just double click. Cumulatively, you have 0 or 1 customers coming. The probability or 0 or the customer separated by 1 minute, the probability is 73%. The customer's inter-arrival time is either 0 or 1 or 2 minutes, it is 91%, and so on. And we notice that, by the time we look at the inter-arrival time of, let's say, in fact, even with the 4 minutes inter-arrival time, at least 4 minutes, the maximum of 4 minutes, 0, 1, 2, 3, 4 is already 99% plus, right? So let's go ahead and start calculating our queuing system now. Right. So the first thing is we have a reference baseline which has everything 0. The 0th customer arrives at 0 time, requires 0 service time, etc., etc., and there is no wait time and so on. So let's look at the first customer. So once it's like you have started your service, when do you expect the first customer to arrive? Right. Now this follows the Poisson process, and we have already calculated distribution of the inter-arrival time. So let's see how do we derive the inter-arrival time. So look up for what? We will just generate a random number, and that random number will look up in this probability distribution table, Command T. And correspondingly, we'll pick up the inter-arrival time. So this will tell us the inter-arrival time. If we don't find, for whatever reason, the formula fails, in that case, you would like to kind of put the average inter-arrival time, Command T, comma, and we are not looking for an exact match. We are rather looking for a match of the next larger item. Right? And since it's an ascending order, we'll just go from search from first to the last. I close this and I get the value. All right. So since now we know the inter-arrival time, that is the time that has elapsed after the first customer or the previous customer arrived. So your arrival time is a simple calculation. When did the last customer arrive? Plus what is the inter-arrival time between the previous customer and now? And this is the time in which your current customer arrived. Right. Next, what we do is once the customer has arrived, we look for the for the conditions to implement our call prioritization. So we check for if, and we look at whoever has completed. We'll check for the end service time of Alice and the end service time of Martin to determine whom does the call get assigned to. So how we do not know, because all these services may start in the ascending order, but the end time may not necessarily be in the ascending order, right? So for that, we will look at maximum of the Alice colon G5 to make the formula copyable. And we will start from the beginning until the previous point. All the end points, we find what is the maximum of it. And we will compare it against, is it less than equal to the max of, since we are saying if both of them are equal and both of them have ended the service, if both of them are available, the call gets routed to the to Alice, right? So we compare this maximum of K colon K5 value. If this is the case, then we say Alice. Else we say Martin. So this is how we determine who gets the call assigned to. And what I've also done is I've applied the conditional formatting so that if it is Alice, it will be green in color. If it is Martin, it will be red in color. So we can quickly identify who is assigned the task. So now we have got the arrival time of the call. We have determined whom does this thing get assigned to. Let's look at the start of the service. So now we don't know whether it is going to be Alice or Martin. So we will use the if formula. If T6, use the command T, so that I'm locking it to the column D. If it is equal to Alice, then we look for max of the end time, all the values here, comma C6. So either if the Alice has already completed the service in idle, it will immediately be the start time. And if Alice is still servicing someone and you're assigned it to service, assigned the call to Alice, in that case, we will have the customer to wait, and that customer will start only after Alice ends the service. If not, then we just keep it blank because Alice is not assigned the task. Right. So since Alice is assigned, so arrival time and this, because Alice and service is 0. Let's say if I make it 5, you will see that it goes to Martin. It's 7. Okay, because the arrival time is changing. Okay, let's keep it at 0. We will study it when we have the more data to kind of play around with this. Let's look at the service time. Now, service time follows the exponential distribution. So we are going to, we actually would need a inverse of the exponential, right? But the way the other functions are available, let's say if I look at binomial, it provides us with the inverse function also. It provides for norm, it also provides the inverse function, right? But if you look at exponential, it does not provide us with the inverse function of the exponential. So what we will do is we will use the inverse function directly. So if this is blank, then we use the formula negative Alice average customer time, command P, multiplied by a natural log of a random number. If not Alice, then we keep it blank. Right. So this is the inverse of the exponential function which I've implemented here. And those who are interested in the mathematics of how this thing gets implemented, they can read about it by searching how do you calculate the inverse of a exponential function. Okay, so let's me confirm. Okay, we need to, if this is, okay, if this is blank, then I have to keep it blank. Else I will apply the formula. All right. So we are able to now determine the exponential time distribution. So here it turned out to be 0.49. And the next formula is fairly simple, is equal to if the start of the service is blank, then blank, else we take the start of the service plus the end time of the service. I mean the service period to find the end time of the service. All right. So service started at 1, it took 0.17 minutes, and it ended at 1.17. Right. Now let's calculate the idle time. If so let's check if this is Alice. If this is Alice, then what we would like to see is the time at which the service ended of the previous one and the time at which the current service started, right? The difference between that is what is going to be the wait time. So it becomes E6 minus max of 5, and we put a dollar here so that it contains it takes the entire array starting from the top. Else we keep it null. Right. So it is showing 2 minutes. The reason is Alice was free, Martin was free, but the customer was not there for the first 2 minutes. So when the customer arrived, until that time, Alice was sitting idle with no calls. Right. We can look at, right. So this time it's 1 minute idle time. This time there is no idle time and so on. This formula seems to work. Now let's see if I can copy the Alice formula for Martin. So I've just pasted it here. And let's check. All right, so this one I need to fix. So let me again go with the first principles. Is equal to if equals Martin. Then take max of this with a dollar sign here. Comma the arrival time. Else nothing. All right. So if Martin is assigned the task, then we see whether Martin was free. In that case, it will be value C6. If Martin is not free, you will have to wait until the time Martin becomes available, and then we have the end time becomes your start time. Let's do the second calculation also. Is equal to if this is null, there's nothing there. In that case, we don't do anything. Else we calculate the Martin's exponential distribution determined service time, T multiplied by the natural log of a random number. So since Martin is not assigned, it will be this. And we do the same calculation for the end of the service is equal to if start time is null, then null. If it is not, then we simply add the start time plus the service time to determine the end of the service time. And now we can easily calculate the Martin's idle time. If this equals, then we take the difference between the start of the service time and the end of the service time of the previous call. We'll take I6 minus max of dollar. Take the difference, else we say nothing because Martin is not doing the job. Right. So let's calculate the wait time. So wait time will be very simple. Max of E6 comma I6 minus C6. Right. So, and we know that, no service can start before the end time of either of these. So we don't have to check for that condition, but this will always be greater than that. So we just look for the start time here and the difference between the arrival and these two start times. All right. So now what we can do is we can copy paste this formula underneath. So it will fill in for all the 500 values. Great. Let's verify whether it is actually doing the job that we are expecting it to do. So let's double click. So we generated a new value. Inter-arrival time is 2 with the reference of 0. It comes after 2 minutes. So Alice is waiting idle for 2 minutes, which we can see here. And Alice is assigned this person, this call, and it starts at 2 minutes and the call lasts for 0.76 minutes. So the total time and time is 2.76. 2 minutes is the idle time and the customer did not have to wait at all. Then the next customer comes immediately with this, with the previous customer. There is no inter-arrival time. So Martin is assigned because Alice is busy with the first customer, and Martin is assigned at exactly 2 minutes. Yes, and it takes 1 minute 10 seconds, and it ends the service at 3 minutes 10. Now, and Martin also was sitting idle for 2 minutes. Now the next customer which coming is again coming together with the second customer. So this guy will have to wait for how long? Till the time Alice or Martin is done, which is 2.76, 3.10. So Alice gets done first. So Alice is assigned at 2.76. It takes so and so time. This is this. And there is a wait time this time. And Alice did not have to wait at all because she finished this previous call and got on to the next call. And then the next customer also is immediately without any time delay. So that guy comes and waits for 1 minute 10 because this guy came at minute 2, and until 3:10 Martin was also busy. So 3:10, and yeah, so all the calculations look great. So now basis this, what we can do is we can now calculate the performance or the idle time for Alice. So the total idle time for Alice can be computed simply is equal to sum of the idle time. So in the overall shift, Alice has been idle with no task on hand is 53 minutes 93 seconds, and the percentage of idle time is the time until which Alice had the last service completed. So that is max of on T down. So 6.28% of the time Alice was idle. That is 29.48 minutes. And of course, this will keep changing because this is all dynamically determined. We can do the same calculation for Martin as well. Is equal to sum of Martin's idle time. Which is 84 minutes 76 seconds is equal to this. This will give us the percentage max of, I mean, the time when which Martin completed his last service. All right, so 10% Martin has been idle, 12% Alice has been idle. Now, interesting thing that you notice here is, though the priority is to assign the task to Alice, still Alice is having more idle time compared to Martin. The reason is the time that Alice takes to complete the task of the customer is much faster than Martin. So as a result, Alice gets to spend more time doing nothing compared to Martin. Let's calculate the total wait time in the system is equal to sum for wait time. So 1394. And the maximum wait time faced by any customer is max of this. So the maximum that any customer had to wait was up to 24 minutes. That's quite large. And the average wait time, $13.21. So sometimes it's very large, sometimes it is small. So 3.26 and so on. So now we will be able to kind of, we notice that, in the previous to this one, the average wait time changed from 13 minutes to just 3 minutes, right? So what we will do next is we will calculate the, we will run this simulation of 500 customers for 100 times. And for that, we will use the data table. So Alice idle percentage is this. Okay, I need to come to the top. The idle time for Martin, this, and the average wait time is this. Right. So what we will do is command shift right down, and we will run data. What if data table? We don't want to give any row input, column input. It can be random because all these calculations are generated through random numbers. So we can just click wherever you are comfortable. And we can see the entire statistics has been filled in here. Now look at the average wait time over 200 runs. So that is something which will be a lot more reliable. Average wait time. The teller one, which is Alice, 10 is equal to average and the average for Martin is so these are actually percentages. So just convert them into percentage representation. Okay, this is 34 to this thing. No, it should actually start from the top. Is it starting from the top? Yes. So this needs to be fixed. Go to the top, come on down. Is equal to average right. So we are calculating from the top. All right, yes. So all three formulas are correct. So on an average, the average wait time is 6.86 minutes. And that's more reliable than looking at those highly varying numbers. And this gives us a understanding that, we have, let's look at, the arrival rate is every 1 minute you have one customer arriving, and their service time is 2 minutes and 1.66. So this is fairly balanced, the average of this. And that's what should actually reflect in the idle time percentages as well. And almost about 10%. And I believe that's what is the margin here. So 2 plus 3.6, 1.8. So it says 20% spread into those two. So 10% each. Each are equally idle. Right. So it will hover around 9 to 10%. That's the long-term idle numbers. So this looks like a good chart. The thing is, we can plot a chart and see how they are varying. And interesting thing is, since we already have okay, so the point is this must go on the secondary axis because this is the average wait time, right? Okay, so this is the distribution of the idle time. So let me just change it to a column. And this orange one is for the Martin's idle time. It doesn't show up very clearly because the number of iterations are way too many. Let me kind of just get rid of this wait time and maybe move it back to this. So it says that it has fluctuated between about 20% and goes as low as just 0% and 1% as well, but hovering around 10% on an average. And fix this by putting it to 100 because we have only done 100 runs. And the idle wait time is largely similar, and most of the time we are seeing Alice is having more idle time compared to Martin. So Martin is slow, so he need to kind of put in extra effort and extra time attending to the customer calls compared to the Alice, though the priority is to assign the calls to Alice. So that's a very interesting discovery from this. Thank you. You can use this model variety of this template can be used for modeling variety of this service call priority by putting in the assignment function here. Thank you.